Hello, everyone. My name is Annika Srinivasan. I am a fourth-year student at the University of Illinois, Urbana-Champaign, studying mechanical engineering. Today, I will be discussing the project I've been working on this summer through Carnegie Mellon University's Robotics Institute Summer Scholars Program, which is on the development of the HapDeltaZ, a 3-degree of freedom haptics educational kit. To begin with, the motivation behind this project is that hands-on teaching enhances student learning and motivation. Furthermore, dexterous active manipulation in particular shapes how people learn. By simulating touch-based interactions, haptic devices offer a low-cost solution for facilitating hands-on learning experiences to teach STEM concepts. However, to our knowledge, existing educational haptic devices are limited in their dexterous capabilities, providing feedback in only 1 to 2 degrees of freedom. Considering this, we propose the HapDeltaZ, a novel, low-cost, 3D printed kinesthetic haptic device that delivers feedback in 3 degrees of freedom to a user's thumb. It enables interaction with virtual objects of varying stiffness, and it enhances dexterity and optimizes the thumb workspace via an integrated, compliant delta mechanism. So what does our overall approach look like? The first step was mechanical design. Specifically, I conducted multiple analyses to select optimal parameters for the compliant delta mechanism. Following this, I worked on the haptic feedback control, generating 2 types of virtual environments and rendering the required forces. Lastly, I evaluated the device's performance through a stiffness discrimination study with 4 participants. As I mentioned, the first step was mechanical design. The requirements of the HapDeltaZ include that it should be capable of enabling feedback to the user's thumb in 3 degrees of freedom, that is flexion/extension, abduction/adduction, and opposition. The design must also ensure affordability and accessibility for use in educational settings. Now, to sufficiently provide feedback in multiple degrees of freedom while allowing for natural dexterous movement of the user's thumb, we implemented a compliant delta mechanism. Delta mechanisms, or robots, are parallel robots capable of translating in all 3 Cartesian directions. They consist of 2 platforms, including a stationary base and a moving end effector, as well as 3 sets of upper and lower linkages that connect these 2 components via universal joints. We specifically adopted the DeltaZ robot's design, which can be seen in the figure on the right. Its delta mechanism incorporates soft lower linkages made of TPU with living hinges, which are joints formed by locally decreasing the width of a material. The delta mechanism is contained in a custom thumb unit, which you can see here in this exploded view of the cat. The base, which houses the motors that drive the feedback, is made of PLA. To move the delta mechanism, the motors, which are encased with caps and fasteners, are connected to the upper linkages via 3D printed clamp shaft collars. At the center of the thumb, we included a mechanical stop to prevent non-ideal configurations of the end effector that may result from using soft linkages. It also assists in calibrating the delta mechanism. We 3D printed all parts of the thumb unit to reduce the total cost. Furthermore, cutouts were created to reduce expenses and printing time. Shown here are pictures of the final prototype in its resting configuration and with the user. To maximize the thumb's range of motion and minimize non-ideal behavior, we had used forward kinematics to simulate the delta mechanism's workspace along the z-axis to determine its optimal dimensions. In particular, 4 primary parameters affect the workspace: the side lengths of each platform and the lengths of each linkage. These served as the inputs to the simulation. One limitation of the forward kinematics, however, is that they do not account for the flexibility of soft linkages. And while there are machine learning algorithms available that account for the deformation of the flexible TPU when establishing the delta mechanism's workspace, we opted not to use these techniques because they are more computationally expensive, therefore making it less accessible for educational purposes. As a result, the simulation was used as a baseline to identify ideal parameters, and then physical experimentation was performed afterward to validate the dimensions used for the thumb unit's delta mechanism and adjust as necessary. In this video, you can see the simulation with optimal dimensions. For the soft linkages, 2 additional parameters beyond linkage length influence the behavior of the delta mechanism, specifically affecting end effector orientation. These are hinge thickness and beam thickness. Optimal behavior requires the base and end effector platforms to remain parallel. We use the same dimensions as the original DeltaZ robot, as they maximize the compliance of the TPU while also accounting for the limitations of inexpensive 3D printer nozzle diameters. These include a hinge thickness of 0.41 millimeters and a beam thickness of 4.5 millimeters. Moving on to the haptic feedback control, feedback was provided to the user based on their interactions with objects in a virtual environment, which were visualized by a graphical user interface, or GUI. We simulated two different scenarios, each involving a sphere. In case 1, which you can see on the left-hand side, the user's thumb is outside the sphere, and if they attempt to enter it, their finger is pushed outwards. In case 2, which you can see on the right-hand side, the user's thumb is inside the sphere, and if they begin to exit it, their finger is pushed inwards. We selected these scenarios considering that spherical grips have been used before to evaluate dexterity for both humans and for robot manipulators. The magnitude of the haptic feedback depends on the distance of the user's thumb has penetrated the sphere's boundary. For case 1, which again is the user trying to enter the sphere, if the distance between the user and the sphere is less than the sphere's radius, only then is feedback delivered. Similarly, for case 2, which is the user trying to exit the sphere, if this distance is greater than the sphere's radius, feedback is delivered. Otherwise, the user feels nothing. Following this, we conducted a pilot user study to assess the HapDeltaZ's force rendering capabilities. Specifically, we utilized two alternative force choice with the method of constant stimuli. For each case, users were presented with spheres of different stiffness and asked which option was stiffer. And shown here are our results. To analyze the data, we fit a psychometric function to the data of each participant for each virtual environment. We then use this function to calculate what is called the just noticeable difference, or JND, which is the smallest change in stiffness a person can detect. For case 1, the JND was approximately 5 newtons per meter, and for case 2, it was approximately 5.7 newtons per meter. These preliminary results suggest that participants were able to consistently detect changes in stiffness in 2 different virtual environments. That concludes my work on the HapDeltaZ over the summer. For future work, we plan to implement mechanical subsystems for the index and middle fingers to enhance dexterity. We will also enable teleoperation of a continuum foam robot hand with haptic feedback. Lastly, we plan to conduct a case study in a STEM class to assess the device's educational efficacy. Now, finally, I would like to acknowledge a few amazing people. Thank you to those who helped organize the Robotics Institute Summer Scholars Program, specifically Rachel Burson and Dr. John Dolan, and for welcoming me back a second time. I also want to express my gratitude to my mentor, Iki, and my advisor, Dr. Melisa Orta Martinez, for the opportunity to work on this project and just for all of your help over the summer. Lastly, I want to thank all of the Shred Lab members and the whole risk cohort for not only helping me during this project, but I needed it, but for just being so inviting and welcoming and fun. Thank you for listening.